Hey everyone, thank you for coming. So in this talk, you will learn how synthetic data might become a key ingredient towards building and testing embodied foundation models. So now by embodied foundation models, I mean general pre-trained models, not for the web, but for physical machines. That's where the body comes in embodiment. And these machines need to act safely, interact physically with people, with machines, and with the rest of the world in many different ways. So let me give you a quick example there. So here you have an example, which is, again, Toyota, so cars. So obviously in these cars, you have perception models. Actually, you have some people here responsible for them. So you can talk to Vadim and others. And so running in all the Toyota safety systems for a variety of tasks involving steering and braking with or sometimes instead of humans, if you're familiar with automatic emergency braking systems. But more generally, also in cars, is not just about perception. You also have hard control challenges. And so you can have, so at TRI, we've been working on controllers that can handle extreme vehicle dynamics, like drifting, because this matters when there's snow and or ice or things like this. And so this is very difficult for control algorithms. And so this is one of the frontiers of research in control. More generally, there are tasks in robotics that also we care about at Toyota. So for instance, robots preparing food, not that we're going to make a Toyota food making robot, but those are very hard challenges for robotics that drive progress. We also have other example of tasks and interactions. So we've made a robot that's capable of doing grocery shopping, over 30% success rate right now. So same thing, not a grocery shopping robot yet, not one sold by Toyota. But the reason we're making it is because, again, same thing as like a challenge task for robotics and drives a lot of research progress. And actually what we already found in our robotics team found is that a lot of these advances transfer to more setups like this, industrial robotics, and much different type of interactions and much different type of arms. And so despite ChatGPT and the progress that's called generative AI now, if you follow the trend, a foundation model that works across all these tasks and all these embodiments that I talked to you about that we're actively working on, such a foundation model does not exist yet. So no, this is not a commercial talk announcing the Toyota foundation model that is the brain for all robots. So if you thought it was this, you can enjoy Vancouver, I guess. But it's a research talk. So there's a lot of challenges towards getting there that I want to talk about. And in particular, because we're a research institute, we're working based on some hypothesis. And so our main working hypothesis in the team is what we call principle-centric machine learning. Realistically, we will never have enough real-world data to let the systems learn everything by themselves. And actually, what I will say is even stronger statement, neither do we want them to. For instance, there's very clear examples in matters of safety. There's certain concepts of safety, like not killing people, you don't want to learn from examples. So and also another big thing is that ChatGPT cannot die. Humans and robots can. So that means it's a fairly different stakes when you go from the web to the real world. And so we want models, obviously, to learn from data, that's still machine learning, but we also want to be able to teach them, right? And teach them what we already know, our principles. And so the question is, that I'm going to talk about in this talk is, how do we do that and which principles? So there are, in fact, a lot of principles, and we've done a lot of research on this in my team. And especially if you're looking at what we know about people already, even just babies, they don't know much, but they have some core knowledge and some experience, and they combine both data and principles to allow them to give rise to neuroscientists, hairdressers, surgeon, mathematicians, you name it. So there's a lot of inspiration to take there. But in this talk, I will focus on the principles where synthetic data and more generally simulation plays a key role for embodied intelligence. So first, I will discuss how you can teach principles when you can program them into a simulator, which we use as a synthetic data generator. And second part of my talk, I will show examples of more directly embedding differentiable principles into the learning process itself to learn to generate synthetic data and use it. And then finally, I'll conclude with a perspective on the many open research challenges to get towards what we desire, which is an embodied foundation model. So the first and most popular technique is to program what we know in a simulator, okay? And we use that simulator to generate a curriculum of synthetic data to complement real data. So to program what you know into a virtual world that you can then generate, you can use to generate arbitrarily labeled data, including all kinds of variations in camera positions, weather conditions, etc. You've seen one of the pioneers in the field talk about this earlier, Antonio. We've also done some work a long time ago in virtual kitty, so recreating digital clones or digital twins, and then altering them and generating data from there. And this is pretty involved. Like programming a simulator like this is actually a pretty involved task, which is why you have since then, this was like CVPR 2016, you have some companies like Parallel Domain that make a business out of it because it does require quite a bit of muscle, engineering, and this is actually pretty involved. But what you get out of this is you get some clear benefits compared to real world data, right? You get quantity, you get perfect labels, although aligning your labels, that's a good lesson. And I think in terms, but you pay a cost, of course, there's no free lunch. And the cost is this infamous seem to real gap, which comes from different kind of like statistical patterns from the real world and the synthetic data. So the label domain gaps is one, but also there's photorealism, but there's also content realism. If you have just 5 types of cars in your simulator, you're going to have a problem when you deploy in the real world. And so the question now becomes, how do we overcome this domain gap? And so the first way is to realize that simulators do not just produce ground truth. You've seen the previous talk or in typical talks is like, it's the ideal data you want, right? It's like data plus the ground truth you want, but it's shortchanging actually what the simulator gives you, because the simulator gives you all kinds of internal states. In the simulator, you know how the world works because you programmed the world. And so those internal simulator states can act as privileged information to regularize learning, to be compatible with how the world works, not just how it appears, okay? And so this is an earlier paper we made a few years ago, where you have your typical losses, including your target loss, your domain adaptation losses, but you also want to maybe have separate head and separate losses to predict these internal states of the simulator, to say, I want you to predict, let's say, semantic segmentation, but I also want you to do it in a way that shows you understand how the world works. And this is very difficult in machine learning, say, what does understand mean, etc. But here in this case, we know what understand means. It means you understand the generative process that you programmed into the computer, because this is literally how the world works. The problem is, this is how the simulator world works. You can't easily do that in the real world, right? I mean, this entire fields of science that are trying to figure out, how the world works. And we generally don't have access to that. We just have access to pixels. And so you can't easily do that in the real world unless you have some way to not fully understand how the world works, but you have some way to encode constraints, encode some principles that constrain the learning objective. And so which is exactly what some forms of self-supervision provide. In fact, we have shown that we can reduce the seem-to-real gap by leveraging geometric constraints about the physics of light. So we don't know the exact solution, but we know how, when we violate physics, for instance, and we can transform those into self-supervised objectives for depth and ego motion estimation on real data. So now this time it's like constraints about how the real world works. And we can do a mixed batch training approach or other approaches. In this case, for the GUDA paper, we did the mixed batch training approach. So I won't go into the details of the architecture, but just to tell you that this is a little bit more complicated this time than just an additional loss, although it kind of is in essence, but you actually need to combine multiple internal models so that they decode for different types of variables. And you're basically doing some form of system identification of how the world works in this case, and geometric parameters that you can then use to make predictions in a way and then regularize them to be coherent with your geometric principles. So a key takeaway in particular in that paper and in that architecture is that encouraging visual features to be more grounded in 3D geometry, it results in better generalization across domains, because geometry and physics of light, it works the same way no matter the domain. And this is in fact a more general observation that we made in our research. It goes actually beyond seem to real. The aforementioned self-supervised view synthesis objective can be used to pre-train general models for 3D vision. So we've been very successful with exploring this in research and more tangibly in practice too, because we found that this approach generalizes really well across many domains, including very challenging ones like in the snow, very distorted fisheye cameras, underwater, where water acts as a very weird lens, inside robots, tactile end effector, the bubble in the middle and lower middle, and in the supermarket also examples that I've talked to you about. More on that tomorrow morning at 9:15 at the Vision-Centric Autonomous Driving Workshop. We also have a couple of people here, Raj, Igor, who are experts on this. They could talk to you about that. So back to synthetic data and privileged information. Some form of ground truth can only be obtained in SIM. And a particular example we have used in our research is to keep track of where all the objects are in the world, even when they're not visible. And for instance, from a target viewpoint, like typical egocentric viewpoints that you may have in driving, in robotics, in AR, VR, etc., you have a lot of occlusions, and losing track of objects due to occlusions is one of the most common sources of errors in perception systems, despite being very easy for humans. Actually, you've learned this when you were 4 months old, when you played a peekaboo game, right? The idea that objects continue existing in the world, even when unobserved, is actually a core cognitive principle called object permanence. As I said, humans learn this concept from a very early age and use it for the rest of their lives, including not just to play peekaboo, but this critical skill for driving safely in dense urban environments. And so taking inspiration from the ways humans learn, we have developed a recurrent video model, conv-GRU model, that can track objects even under total occlusion, thanks to leveraging privileged information from synthetic data. So going back to having some unique information when you're in synthetic land and using that information to your advantage. In fact, we have also shown in our ICML paper that object permanence can emerge from random walks along space-time feature graphs. And we've also shown it that it can work through occlusions and containments. So when an object disappears because it's contained in another one, it's a bit more complicated because this time you can have an object move another object, even though the contained object is not visible. And so we have a paper on that using video transformers later this week at CVPR. And so in all those cases, one thing that we have found, we actually found two things that were important for performance when using synthetic data. First, explicitly modeling visibility, right? So the stupid mistake you can do, and you don't need to do it because we did it, is to basically just say, I have perfect ground truth, I know the position, even when it's occluded, just supervise that, right? And obviously what you're asking the model here is just to hallucinate. And to say, you know, like, this is eye, this is now still an eye. No, this is not an eye, this is a hand, right? But the eye is still there. And so essentially when you're in 2D here, you have some limitations of just using blindly the supervision like this. So you need to explicitly model visibility, which you can easily do by adding a separate head and predicting a visibility flag, which you can then use also at inference time in the tracker. So first one is exploiting visibility. The second is carefully designing the learning objective for fully occluded objects. Again, you don't want to just hallucinate the ground truth position. You want to leverage the ground truth position to engineer an objective that kind of makes sense. And we've done everything from like 3D constant velocity to things that are a little bit more complicated in the case of containment. Another important and complementary way to overcome the seem to real gap. So far I talked to you a little bit more from the angle of machine learning, which is like domain adaptation, right? Statistical alignment of domains and things like this. But there's obviously a big effort, and the reason why this community is still thriving is because simulators keep getting better, right? Whether commercial offerings or open source simulators. And so rendering has greatly improved. I think obviously if you saw the earlier Unity, VKT, kind of like not so great graphics, and now things you can do. There's a clear gap in performance, but there are still some hard challenges in accurate dynamic simulation, which matter a lot for robotics. And so that's why it's been a really core aspect of our research at TRI, especially in Rusty Drake's team, which develops the Drake toolbox, which you can find online. And by the way, just getting the better simulation and the statistical alignment doesn't have to be in just a position. So you can actually, in opposition, sorry, you can use them in combination. For instance, with domain randomization approaches, like this one that we published at ECCV last year on photorealistic neural domain randomizations, which provides me with a nice segue from pure programming of a simulator to learned synthetic data. And so we just saw some techniques to leverage what we know in a programmed data, a synthetic data generator, right? That can complement real data. But what if we don't know enough to program it explicitly in a simulator, right? If you don't have the simulator in the first place for what you care about. So in the second part, I'll discuss how we can instead learn to generate synthetic data based only on partial knowledge. So this is basically the reverse process of what I've shown so far, which is learning how to simulate reality, or real to sim for short. You probably heard this expression. The technique we use here is related to a core cognitive process called analysis by synthesis. And put simply, analysis by synthesis is like the scientific method. You all have this running in your head, maybe even right now. You just make a hypothesis from the incomplete knowledge that you have, and then you falsify or verify it, and then you just iterate. So let me give you an example from our own research on object modeling. Imagine you want to detect where various objects are in 3D from just an image. So this is here the example. So normally you would need a lot of manually labeled examples of images to train the model. And there exist such data sets, I mean, mapillary vistas, etc. And that's what people typically do for 2D detection, but this is actually really hard to do in 3D. You need additional data, additional information, forward, backwards. It's a lot more complicated. But 3D is actually what we care about, and what we've pushed actually in state of the art in research for several years now. We're presenting actually a paper later today on that called VEDET. So instead of requiring a lot of 3D labels, what we're doing when it comes to real to sim or analysis by synthesis, we instead, as I mentioned, make guesses of where objects could be in the scene. That's our hypothesis at the start of this animation. And then we rely on geometric principles to render these guesses and see if they align with the data. If they don't, we adjust our hypothesis in the right direction, which is with this little wiggling animation you're seeing. And this is where the combination of data and principles happen. The way this is done internally is it's all thanks to differentiable priors that are learned in general from synthetic data, for instance, from CAD models. So in general, neural fields, what's now called neural fields, like our coordinate shape space model shown before, or more recently, our ROAD model. ROAD stands for recursive octree autodecoder, which is shown here. They provide a strong framework to learn differentiable priors, in a sense, kind of like mini simulators, if you want, but in a neural network. And they're used for analysis by synthesis by learning or learning by re-rendering, because they're differentiable simulators. So we don't do it just for shapes, like the few ones I've shown you before, but we do it also for fully textured objects, like in the Chapeau paper that we presented last year, you can see on the left. Also for not just for textured rigid objects, but also for articulated objects, like the paper the team is presenting on the right called CARTO. but also for multiple type of objects and different types of neural rendering, including dynamics, which is a paper done with our Stanford colleagues, presenting a bit later this week. And it's not just for shapes and not just for objects or multiple objects, but it can be for whole scenes. And not just scenes holistically, like what we would do, for instance, with monodepth type of models or 3D just reconstruction models, but actually can do it in parts, like the single shot scene reconstruction paper you see at the top, or one we presented recently at iClear on neural ground plans, where we can decompose either the background and the foreground, or we can decompose the ground plane and the objects on top of it, the static and the dynamics part. So I've given you pointers to our research on how we use both programmed and learned synthetic data. So now I want to just wrap it up and open up with a few perspectives. So to sum up our current implementation of principle-centric machine learning, we use fundamental principles to both generate synthetic data in a simulator we can program, but also reverse engineer real data with simulators we can learn, differentiable priors. And this real to sim to real iterative process, right, creates sort of a learning flywheel, combining knowledge and experience, principles and data. Now, there are still some difficult challenges that this approach faces. The first one is when we don't even know what objects to synthesize, which is the things you see at the top. So we have a couple of different papers. Maybe I should hide this. But we have a couple of different papers on this, on unsupervised object discovery, where, again, we use synthetic data for a lot of these works. So both at last year's CVPR, but also at this year's CVPR, object discovery from motion-guided tokens, which is going to be presented this week, which you see at the top. And also, there's some more challenges when not just you don't know what objects you care about. It's like let's assume you know, but you don't even know how to simulate them. And this is actually, when you look at driving, you don't care about this maybe too much, but when you look at robotics, now this becomes a real serious problem when you're doing things like cutting celery or breaking eggs. I would argue even in driving, when you have like debris on the road or collisions or stuff like this, this matters a lot. And so there's a new benchmark and a new challenge we're proposing on this this week in the paper, Breaking the Object in Video Object Segmentation, and the VOST challenge. Another really important area of focus for us, and an area that I would encourage more research in the community in general, is safety. As shown in the many papers we're publishing in that domain. And for a lot of these papers, simulation actually plays a huge role here in testing and developing our methods. And you've seen this actually also in Antonio's talk. One work I want to particularly highlight is our IDBF paper on the right, which stands for In Distribution Barrier Function, which actually just won the Best Paper Award at L4DC, which is the Learning for Dynamics and Control conference that's just happening this week at the same time. And in this, we proposed a novel approach that prevents learned visual motor policies, so the type also that Antonio talked about, but we try to prevent them from drifting out of distribution by leveraging cutting-edge concepts from control, especially control barrier functions, but generalizing them from state spaces to very high-dimensional learned latent spaces using also self-supervised learning. So this is a very rich area of research, which I highly encourage you to all look at. So in summary, my team at TRI is working on embodied foundation models. We don't have one yet, but we're working on it. That factors in all these different tasks, all these different considerations, all these different embodiments, and doing it safely. And because we work with physical systems, we never have enough data. So we need to combine with principles, both in vision side of things, but also in the interaction side of things. And that's where physical interaction with the world, with people also is really important. This is most of it is not my work. It's a lot of people's work, actually, both in the team and a lot of university collaborators. We're fortunate to have a very large university collaboration program, which is also why we have a lot of papers at CVPR this week. This is just a list if you want to screenshot this, or you can go at our on our Medium blog post to see all the different papers we're doing this. Yes, because an embodied foundation model is not one model. It's not just ChatGPT. It's a very complicated system. And a lot of these has code online, data online, the papers, and more details. And with that, I'm happy to take any questions. You want me to repeat the question? Yeah. So you said that input gap is practically useless unless addressing the label domain gap. Addressing the input gap is useless unless addressing domain gap, label domain gap. Any info on the input adaptation after you do label adaptation, is it useful then? Yeah, so I mean, I guess Philip has some answers to that. As I said, or as he said, very few people actually pay attention to the label domain gap. So, but generally we do by making sure that the labels make sense. So it's not discussed enough in the paper. It's kind of more like dark knowledge that people do when they design the data sets. So when you do that, yes, input domain gap is actually really important. It depends again on the quality of the simulator. Antonio talked about some techniques. We also have some techniques there. So yes, it does matter how you do it. And the first part of the talk, I talked about how you can use privileged information from the simulator to overcome that input domain gap. By using internal states of the simulator, how the world works, not just how it appears. And then the second is how the world works or the constraints in the real world using self-supervised techniques, self-supervised losses in the real world. Yes, they do matter. We might be under discussing the label domain gap issues, which is a fair point. But there's a reason the community is focusing a lot on input domain gaps, is because there is a gap.